So quantum numbers are, again, numbers that arise when you solve the Schrodinger equation, and these are quantities that are restricted. So the adjective quantum means restricted. There's only certain allowed values for these numbers, and there are numbers that are associated with orbitals. In fact, you can think of quantum numbers as ID numbers for orbitals, a way to identify these orbitals. So there are many different orbitals that you can use to describe an electron, and so we make distinctions between these using quantum numbers. A unique set of quantum numbers is a unique set of ID numbers, you might say, that we can use to describe an electron. Okay, the symbols we use for these quantum numbers are N. N stands for what's called a principal quantum number, and it has to be a positive. It's restricted to positive integers. That means these can only be 1, 2, 3, 4, 5, and so on. Okay? It can't be 0, it can't be 2.5, it can't be -2. It has to be a positive integer. There's also a quantum number called the orbital quantum number, or the angular momentum quantum number. This gives us information about a property called angular momentum for an electron, and this is represented by lowercase l, usually written in script. Okay? And the restrictions on this orbital quantum number is that it has to be a non-negative integer less than n. What does that mean? If n is, for example, 4, then the allowed values of L would be an integer less than 4. Okay, so 0, 1, 2, 3. Okay, those are the allowed values for L if n equals 4. Okay, if n equals 10, what are the allowed values of L? It will be 0, 1, 2, all the way to 9. Remember, 0 is a non-negative integer. Okay. Now, there's a third quantum number called the magnetic quantum number, and that is something that gives us information about magnetic properties of an electron. Okay, and it's represented by the letter M, or M sub L. So that's M with a subscript L. And the restriction on this number is that it has to be an integer between anywhere from -L to +L. So for example, if L equals 5, then your M sub L, or your M, can be anywhere from -5 to +5. So it can be -5, -4, -3, -2, -1, 0, +1, +2, +3, +4, and +5. It can't be 1.2. It can't be -6.1. It has to be. It can't be -6. It has to be between -5 and +5 if L is 5. All right. So let's see if you got those rules. Here's a summary of the rules. Okay. N must be a positive integer. L is a non-negative integer that's less than n, so up to n-1, from 0 to n-1, and M goes from -L to +L. So which of the following is an allowed value for the quantum number n? Okay, so let's just look at our rules. It's going to be 1, 2, 3, 4, and so on. So it can't be 0. It can't be a fraction. It can't be negative. So the allowed value 2 is one of the allowed values for the principal quantum number n. Let's take a look at this one. Which of the following is an allowed value for the quantum number L if n equals 2? So if n is 2, L can go from 0 to 1. Okay? 2 minus 1 is 1. So the highest possible L is 1. So your L, if n equals 2, L can just be 0 or 1. So 0 is allowed. -1 is not allowed. 1.2 is not allowed. 2 is not allowed. How about this one? Which of the following is an allowed value of the quantum number m if n equals 3 and L equals 2? Okay. So what are the restrictions for L? It has to go from -L to +L. So if L is 2, that means M can go from -2 all the way to +2. So negative 2, negative 1, 0, plus 1, and plus 2. So which one of these is allowed? So negative 3 is not allowed, 1.5 is not allowed, 2 is allowed, and 3 is not allowed.